Alright, let's continue with random variables. In 15C, we already covered the um, expected value and standard deviation. Now, to link that to sort of a real life application is looking at the sample mean. So the first thing is through simulations, and we'll do a case using a CAS calculator. You generate a set of data. So we use simulation to see what kind of distribution you have, not for the random variable, but for the a series of samples. And what we do is we focus on the means and its distribution. The case we're looking at is we have a original random variable. It's the IQ. It's normally distributed. We look later what is a normal distribution. We haven't covered that yet. With a normal distribution, two values are important: is the mean and the standard deviation. Now, from that, what we can do is use technology to generate samples. So let's say we want to generate a sample that has a size 10. Okay, so it's a small sample. Okay, but the advantage of being small is you can generate as many as needed, and they're random. So every time you generate a sample of 10 scores, you get a set of values. From that, you can calculate the mean. So remember, the mean is the sigma means is the sum, so it's the sum of all the values divided by the number of values or the total frequency. In this situation, because it relates to the sample, it's what we call the sample mean, and that's the notation. So it's x with a bar on top. We evaluate the sample mean, and that's what we get for this particular sample. If we do generate another sample through simulation, we're gonna get different values. Therefore, the sample mean is going to be different. Okay, so keep in mind, we get sample means, we generate a series of them through every time we create a sample through simulation. Now that sample mean will varies depending on the sample, and what we do, we are gonna associate to that the random variable. So it's a capital X with a bar on top, and it's the random variable linked to the sample means that we get from every sample. So it's a statistics, it's calculated from the sample, and from that we're gonna get a probability distribution of that random variable. That is called a sampling distribution. And again, sorry, I'm in the way, so if you wanted to read the rest. Okay, so here with a CAS, you should be able to generate random samples. So you're gonna need a spreadsheet. In the first column, the grade one, you can enter formulas, and when you generate formulas, they will fill in the rest of the column. You probably need to follow the orders by giving it a name, and the function we're gonna call is random norm. It follows a series of 4 values. The mean and standard deviation of your original random variable. So here we're talking about the IQ. The mean is 100, standard deviation is 15, and then we specify the sample size. How come the value is different here? Okay, that's a 10 here, and now I put a 25, and then we will fill down. That should be 10, so it's a size 10. That should fill down 10 here, and you fill down, it will fill down the that table. Then this is kind of a different way. You're gonna need to apply that, but anyway, once you have generated your column, you should be able to generate a dot plot and a distribution, and you can see it's kind of normally-ish distributed. It will also depend on the number of samples you generate. So here in that example, they generate 500 samples. Just go back to the textbook if you're interested how to generate that graphically. All right. Previous example, we generated 500 samples. Notice how here we're going to talk about the sample size. So 25, 100, and 200. 25 seems to be a little bit more random, and as you increase your the size of the sample, you tend to get a distribution that gets close to your original random variable. You just keep that in mind for later. I know at the moment it doesn't necessarily make a lot of sense, but that's the pattern or the effect that you get. Alright, so what I just said just previously, alright, one example for this exercise. So pause the video to have a read and attempt this on your CAS. Alright, so it's a normally distributed. Okay, we'll see the function in a minute. It's the mean is mu. So that notation mu is for the original random variable. We're not to the sampling, the sample mean and its distribution yet. We start with the original data and its standard deviation. So the first two, you need to generate some samples. So it's really about implementing CAS. So with the first one, you're going to use random normal to generate. So it's going to be standard deviation, mean, standard deviation, and the size, and it will fill that in. Doing some statistical function. I'll probably talk about this later in class. It's through the statistics functions. You can, when you have data in one row, you can extract all that information. So here from that, you get you have your sample means, and you're gonna get, which is a distribution, you're gonna get the mean and the standard deviation here. I think we're gonna look at sigma x for now. Very little variation, but there is a difference between the two. Oh, hang on. Unless it's sx, I'll come back to it. It's either one of the two. They're pretty close. For part B, again, you will do similarly to this one. You generate that data, but you change the sample size, and then you get the statistics from that new data, which would be here. All right, and what you will notice, they will have a very similar mean, but then as you increase the size, you can see the size of the standard deviation decreases as the sample size increase. So in size 20 to size 50, so let's go back. Whichever I pick, so that's a size 20, that's part A, so it's a size 20. Here is the standard deviation, 0.47, whichever it is. Now for this one, it's going to be a size 50, which is not displayed, but now you can see it's 0.27. So then it links back to that graph. When you increase the sample size, your standard deviation decreases. So here it's really spread, so you have a higher standard deviation, and as you go down to a higher sample size, it gets more clustered as it's described, so it's a smaller standard deviation. Okay, and that's really it for 15C, and I'll see you in the next video.